Welcome to lecture 28. We'll be covering application. So we'll be looking at torsional problems again. We looked at it before and we considered a torsional bar or bar that's subjected to a torsional load. And we discovered, we looked at the assumptions first. And the first thing that we assumed was that the XY plane, so which this is the XY plane here, that XY plane will rotate rigidly about the Z axis. So every point here is moving rigidly at some angle, which I call alpha Z. And so when Z is zero, there's no rotation because we're fixing this plane at the very end at Z equals zero. And then the rotation away from that point is alpha Z, where alpha is a constant. And so we're keeping that rate of twist constant across this bar here. Um, and so we also talked about the cross section is allowed to warp out of plane, and then we're also using the small strain assumptions. We can actually use a more advanced small strain assumption if we wanted to. And so we went through the derivations. We used the principal virtual work, and we calculated internal virtual work and external virtual work using those assumptions. And when I used that, I found these to be the Euler-Lagrange equations, which when I look at them, they're not particularly useful for what I want to do. And really what I want to do is I want to be able to calculate torsional constants for various problems, and I want to be able to determine how much warping I get. And in addition to that, I want to determine what is the rate of twist. All that will be very useful, but I'm not able to get there particularly with this approach. And so for that reason, today I'll be introducing a different approach, and that approach is using the total complementary energy functional. And the benefit here is that perhaps we can come up with an approach that can allow us to get there quicker. Now, we know from the Euler-Lagrange equations that have to satisfy this equation. And so that's the equation I have to satisfy. So let's look at that equation again. And so I'm going to say, well, that is a equation I want to satisfy. So can I come up with a stress function of some kind that satisfies that automatically? So in the case of plane stress, we could satisfy that using a stress function. So use a stress function. And I'm going to call that stress function C. And I'm going to see that stress function C is statically compatible stress field. And so at the lateral boundary, we already covered that. This is my cylinder. We already said that on the lateral boundary, on this lateral boundary, the traction in that lateral boundary is zero. We already said that. Where here, V here corresponds to the surface normal to that lateral boundary. And so the conditions of equilibrium have to be satisfied as well. But a good stress function to select here is sigma xz equals G alpha partial psi y. And I don't know the stress function C. I don't know it. I don't know what that is. We'll try to determine that. Yz equals minus G alpha partial psi respect to x. And I don't know alpha and I don't know psi. Fine. The bottom line is when I plug this in into this equation, you'll find very quickly that this will be equal to zero. You can check it quick yourself. Here you have basically G alpha C comma XY, and then you have minus G alpha C comma YX, and doesn't matter how you take the derivative, that's zero. So it works out. It satisfies, this assumption, it satisfies very nicely the equilibrium equation. And this C here is also known as a Prandtl stress function. So I'm able to come up with these equations that, these equalities that are able to get us there. And so I also want to show that at the boundary, because the traction is zero at the boundary, that means that, if you recall Cauchy's relationship, states that we have T, I, sigma ij, and j. We know that. And we know this is zero for our situation. And if we look at one of the equations, there's three equations here. If I look at the equation for z, we also know that sigma zz is zero in this theory. So I can quickly calculate what I have. I have sigma xz n, let's see. Yeah, I mean, I have n x plus sigma yz and y equal to zero at the boundary, at the lateral. And so if I substitute this Prandtl, these equations here that I came up with into this equation, I basically get G alpha parenthesis, and then I have partial of C comma Y. Let me use comma Y. So anytime I say C comma Y, that's partial Y respect to Y. And I want to use C comma X and same C respect to X. That's what I'm doing. So it just makes it easier for me to explain everything, if you don't mind. And I will then have C comma Y and X minus C comma Y and Y. And this equal to zero. And if I look carefully at that surface here, this surface here, right? That normal is really, nx is really dy ds. And that normal there is ny equals minus dx ds. So to see that, I hope you can see that with me, but if you don't, you can just look at the cross section, right? And this is ds, right? So if I want to look at what dx is, and that's dy, right? And this angle is beta, say, I can calculate that normal, right? I can calculate that normal. And you can quickly see here that the cosine beta here is dx or dy ds, which is really the normal nx. Okay, so that's this here, nx. And it can also verify with me that sine of beta is dx ds. And I'm really looking at this right here, this normal there. And you can quickly verify that nx or ny equals, I'm sorry, yeah, that's correct, is the minus dx ds. You can check it. We won't go into the extensive derivation now. I invite you to pause the video and kind of think about it. But this is what I get, and so I could use that information to kind of expand on on that traction there, that equality. So looking again, at the lateral traction, because I'm not applying any tractions on the boundary, we really have G alpha C comma Y nx, and I know what nx is. I found that was a dy ds minus c comma x, and now I already have plus because minus and minus is plus, so it's z comma, and then I have dx ds, and that's equal to 0. And then I'll do clearly, clearly you can see here that, let me write it differently so you can see it better. You're going to see exactly what I'm going to say. If I look at this carefully, this is really the partial of C respect to ds. If I look at that there, because that's really chain rule. So I just apply chain rule really. So in reality, when I look at that traction on the surface, that traction on that surface implies this equation. And that equation, when I look at what nx, ny is physically, when I look at it at a curve, on a curve, that's just simply the partial of C respect to S. That's really what it is. There's nothing more to it. And so as a consequence, if G alpha is not 0, then I must have on the lateral boundary the partial CS is 0. But in reality, and that's on the boundary, on the lateral boundary. So we conclude then that C must be constant at the boundary. So we're going to then, for simply connected domain, typically, when you have this situation, there's no loss in generality in taking C equals 0. So we'll take C equals 0 for a simply connected domain. Without loss of generality. So that's the assumption we're making. Not an assumption, but it's actually a good assumption to make. And we also want to note that what we're really doing here is applying tractions on this surface here. We're applying the tractions here on this surface. That's the surface we're applying the tractions to create a moment. We're trying to create a moment there. Okay, that's the problem we're trying to solve. So here, what I've done multiple things. I've already shown you very powerfully, actually, very cool, by creating this stress function here, Prandtl stress function, and coming up with this function. I actually satisfied this one exactly, and I satisfied that one exactly. You can see that there. So that's amazing. I came up with a Prandtl stress function that satisfied this and this exactly. If you worked on the area stress function for two-dimensional problems, this is a very similar way. This is similar to the area stress function in that I'm satisfying the governing equations almost, exactly how I want it. So with that said, now we can now start expanding a little bit more, if you don't mind. We can start expanding a little bit more and trying to determine what is going on for our problem. So let's look at the total potential energy, but the complementary way. So again, these stress functions here satisfy the equilibrium equations exactly. So there's no approximation here. It satisfies that exactly. And not only that, I can satisfy this lateral boundary exactly, which remember, typically, we didn't do that. Typically, when we solve the problem, we solved it so it will approximate the order Lagrange equation and the boundary condition, the natural boundary condition. This is a natural boundary condition. Right? And in reality, when you go to the total complementary energy, now we're satisfying those exactly. And what I'm going to approximate then is the displacement field. So again, in the total energy, total potential energy, when you're using that and you minimize pi, the essential boundary conditions there are the kinematic boundary conditions, and the natural boundary conditions are the stress conditions. And the Euler Lagrange equation will be some sort of stress equation like you see here, right? But when you go to the total complementary energy functional, the Euler Lagrange equations are typically something to do with strain deflection relationships. You haven't seen that except once when I derived it in class. I derived the total complementary energy functional and I minimized it, and you saw that I got the strain deflection relationships. So the Euler Lagrange equations there are here are going to be strain deflection relationships, but those are the ones I'm approximating now if I were to use Rayleigh Ritz or something. And the essential boundary conditions are really the natural boundary conditions I had before, which is the tractions now, while the natural boundary conditions become now the kinematic boundary conditions. So again, you have to have a really good understanding of calculus of variations to really understand what is essential, what is natural. So when I now calculate pi star, which is the complementary total potential energy, I'm going to have pi star and pi star is a 1/2 triple integral sigma xz, and it's really without a 1/2. Well, it's 1/2, but I have twice epsilon xz. So may as well just, eliminate. Well, I'll just keep it there so you remember it. I have the d volume. And then I don't have any body forces, do I? No body forces. And then I have traction forces. Traction forces. But the only traction force I really have is the one that causes that moment here. So if this is my cylinder, and this is z equals 0, and that's z equals L, the only place I'm looking at traction being applied is there. So that surface really corresponds at z equals L. That's really what it is, right? That's the only one I have in reality. So we can now do two things. We can use, hold on. Okay, good. We can now employ Hooke's law. So use and we know, what do we know about Hooke's law? Hooke's law tells us that sigma xz equals twice g epsilon xz, and sigma yz is equal twice g epsilon yz. So that's what it tells us, and that's what we've plotted. We're showing. Okay, let me make sure I'm not missing anything. We also can look at this more carefully as well. So let me just do it step by step. Pi star now becomes 1/2 triple integral, and then I have the g can factor out. Why not? And I have now the pi star has to be in terms of stresses, right? The complementary version. Sigma xz squared plus sigma yz squared. And now I have dv, which I could make it dAdl dz. Okay, so this one goes from 0 to L, basically. And then I have, right. Then I have this integral here, Ti ui. Now we know what that is. We know what ui is in our theory. U equals and V equals. I believe U was, well, I don't believe anything because I can't remember, so I have to look it up. U is alpha z, alpha yz, And this, I believe, is minus alpha xz. Hopefully somebody can check. Or maybe this is minus s plus. Yes. I apologize for having to pause there for a second. I did get confused, I admit. And then now I have t. So now I have to do this dot product tx alpha yz, and that's minus, plus ty what? Alpha xz. And the tz does not exist. I'm not applying tension on that surface. And that's evaluated at z equals L because I'm looking at this surface alone. That's the only surface I'm looking at. And so if you can actually calculate what Tx and Ty are in terms of sigma x z and in terms of sigma yz. We can do that. So we can use Cauchy's relationship. Sorry about that. Apologies. And a normal vector is 1, 0, 0. Sorry, 0, 0, 1. Using Cauchy's relationship. Why? Because I'm looking at this surface right here. So in reality, the only thing that's going to show up is this column vector here. So that's sigma xz, sigma yz, and sigma zz, which is 0. So when I multiply these out, I really get sigma xz, sigma yz, and that's 0. Because sigma zz is 0. So therefore, I can plug it in. I can bring the alpha out if you don't mind. Why not? And the L factors out as well because z equals L there, so alpha L. Please correct me if I'm wrong. I already evaluated as equals L, so I'm done there. And so now, yeah, that's it, complementary potential energy. So what are we trying to accomplish? Let's try to remember. So I used the principle of virtual work and I came up with these equations, but these equations are not very useful. I mean, they are useful, but they're not letting me figure out how to come up with torsional constants for the various cross sections. If I apply a moment, I can't really figure out what the warping is, and I may not be able to calculate the rate of twist based on these equations because I am getting some equations are not very helpful. And so I'm using a total complementary energy functional because in this way, if I can come up with a stress function that satisfies the Euler Lagrange equation exactly, and this does, it satisfies the Euler Lagrange equation we see here, then perhaps I can come up with a way of approximating and coming up with torsional constants, the warping functions, and things like that using a different way of going about this. So yeah, so that's what we're trying to accomplish. So I'm going to go ahead and plug in the Prandtl stress function, plug in. stress function which satisfies the Euler-Lagrange equation in PVW. Exactly. And notice that the Euler-Lagrange equation in the complementary potential virtual work or in the complementary total potential energy, the Euler-Lagrange equation will not be the equations, the equilibrium equations. They'll be the strain deflection relationships instead. Okay, very different thing. So I'm going to now go ahead and plug in this relationship here and that relationship there into here and into here and into here and into here. I'll get G alpha squared, obviously, in several locations. So let me go ahead and plug it in. I also have this integral from 0 to L dz, and you can see that none of this stuff here depends on the on z, right? So you can look at our stress functions do not depend on z. Okay, so I can basically have a factor L come out from there and not have to worry about that. Is it correct what I have? Yeah, it is correct. Minus alpha, and I have alpha squared again because I'm going to plug in all this stuff in here. So I get minus G alpha squared again times L. So that looks correct to me. Integral over the cross-sectional area. But now I have minus C comma Y times Y plus C comma X times X. Okay, dA. So that's what I have. I think that's correct based upon what I have here. Because when I plug it in, I have alpha squared, and then I have these derivatives here, right here. That derivative and that derivative. So it looks good to me. If you see an error, please interrupt me, because I don't want to make a mistake. I want to do it correctly. But so far, so good in my opinion. Yeah, this looks good to me. And so now I'm going to do a little trick. I'm going to integrate this one by parts. And I'm not pretending you guys should have known this. It's something that was discovered back in the day, that we could do this and perhaps that'll get us somewhere. And so the surface integral becomes minus G alpha squared L. And now I have plus, ooh, but that's 1. Isn't that 1? Ooh, that's 1. Isn't that 1? Ooh, that's plus 2 sigma, 2 psi. Interesting. Interesting finding. Unexpected for some of you probably. And then I have the fact that I have, and then I have the counter integral. This one is the counter integral. Anytime you integrate a triple integral, the boundaries will be a surface. When you integrate a surface, you get the boundary becomes a counter integral. Anytime you integrate by parts a curve, then the endpoints become the boundary. So let's make sure we get that straight because somebody will make a mistake in the exam, and we want to make sure we're doing it properly and accurately. Okay, very important consideration that I really want we want to make it correct, and that's a counter integral now. struggling a little bit here with writing. Okay, so that's what we get. Very interestingly, we notice that we said that C is 0 at the boundary. We said that. So if this is my torsional bar, we already stated that at this traction, at this surface, C is 0, so that I can make sure tractions are 0. We showed that. Well, guess what? This is 0 at that surface. So therefore that goes away, because that's a contour of the cross section. So therefore everything simplifies a little bit easier now. I get pi star, and now I get something simpler as G alpha squared L divided by 2, double integral, and then I just simply have over the area C comma x squared plus C comma y squared, and I have minus 4 times C, because I have this, I put a 1/2 there, that's why. That's all I get. It simplifies to that, and remember that this is also known, if you didn't remember, this right here is also can be written as gradient of C squared. It's the same thing. Very, very, very cool. I'm very excited. This is supposed to be Y, not X. And hopefully I don't have any errors whatsoever, because I don't have notes on this. Typically, I've been doing it fairly ad hoc. So I apologize for that. You may look at my notes and not find them there. But I think I want you to also notice how this depends only on C. And it's a function also. I should put brackets. And if I want to be even more perfect, let's be perfect, so you remember how this works. A function of pi star depends on a function C, and the coordinates are x comma y. Just to really learn how to do it correctly from, like just 100% correctly. So very cool. That's what we got. So for the viewers, I want to make sure that it's understood. I made an error that was caught, and here I have a minus and a plus. So here, if you recall, this term, sigma yz, was selected to be the minus. And why was selected to be minus? You can see I have a minus there, was so that this could go to 0. Otherwise, it would be plus, and you get twice G alpha. And I want the static equilibrium equation to be satisfied exactly. So that's why we did that. And that error carried here because I had a plus, but it's supposed to be a minus. And so that was an error on my part. That's minus. And so that's where I have a minus and a minus. And that's why you get twice positive here. So everything else should be correct. I apologize for the error, but it just takes a lot. As you can see, even when you don't know the subject very well, it takes a lot of attention to detail, and it can be painful. So I apologize for that. Why we don't look at the Euler Lagrange equations implied by these, so if I want to know what are the Euler Lagrange equations implied by this, what are the Euler Lagrange? Implied by extremizing pi star. So we know how to do that. We find the first version of pi star, and I'm going to only do it. I'm only doing it so that I'm basically doing it to keep showing you how this works. But in reality, this should be a good exam problem actually, if I wanted to. But I think it's worth for us to do it so you can see what it looks like. I'll just do it in one shot if you don't mind, since I know how to do this. And hopefully this is correct. I've been making mistakes. I really apologize. And hopefully my first variation is correct. And all I have to do now is integration by parts. I'll do it for one term, and then I will not do it for the other term because I can just do a little trick I'll show you. And I like doing this to say, okay, I can use it for x and y because it's the same thing. It's going to repeat. This is equal to 0. I apologize. The first variation of pi has to be set to equal to 0. And remember, pi, I'm varying c because it only depends on c. So then I have del pi star equals, and I have g alpha squared L. And then the twice cancels out, so I don't have that twice. I have only the minus c comma xx minus c comma yy. And then I have minus 2 del c, the area. And then the boundary term just becomes, if you don't mind, I'm going to say that this term, this coefficient cancels out. That way I don't have to deal with that coefficient. I'll just cancel the 2 out at least so that it just becomes a little bit simpler. I don't have to carry these things anymore. So that'll make it everything a lot simpler. So then I have the counter integral now with c comma x and x plus c comma y and y del c equal to 0. But c is specified at the boundary, at the counter. So if this is a torsional tube, sorry, not tube, but the bar, we already stated that this boundary c is specified. So therefore, del c is 0 at that boundary. And so what I get, in fact, is what do I get? By the fundamental for any arbitrary variations of c, then I get what? Let's just make it all positive. Why not? That's what I get. And I actually don't like, I mean, I did call this the gradient squared, but I personally don't like writing it that way. I don't want you guys to get confused. But this one I think is worth writing it this way because you guys have seen this as a Laplacian of the problem. You've seen that before. And this right here is really implying, and it has a lot to do with the kinematic compatibility. This is directly related to kinematic Very good. So that's directly related to the kinematic compatibility. And yeah, so that's where we are right now. I also want to do a little trick to kind of remind you what epsilon xz is. I think it's worth looking at that. Or we can just leave it like that and move on, and I'll bring it up later. But this is your Euler Lagrange equation. And if I were to use Riley-Ritz, notice how I'm satisfying this equation. Now I'm approximating the solution to this equation. And approximating the solution to this equation implies I'm approximating the solution to the stress that I'm applying. Okay, so hold on. So we've shown that on the boundary. So that's the Euler Lagrange equation on the boundary. C equals 0. Okay, and I wanna remind you something, because we haven't talked about the moment at all yet, but it is there. That's the moment right here. It is there. It's just we haven't really talked about it. But why we don't go and remind you what the moment was? The moment we've had stated that this is a moment right here, right? That's what we had stated. And so I would like to look at that again, because I don't think we haven't substituted the Prandtl stress function here to see what will happen. So let's do that so you can see what happens there. Because right now we satisfy the Euler Lagrange equation. That's your Euler Lagrange equation. I write it here. But I haven't talked about the moment, what to do with that moment. So let's look at that moment calculation. And as you saw in that page, ML equals I'm concerned I had an ML. Yeah, so I have to write the whole thing. And please correct me if something looks wrong. And I'll substitute the Prandtl stress function. And I apologize for putting that little squiggle there. But now what I get there is G alpha, if I substitute it, isn't that what we got earlier a little bit? I remember seeing that term, interestingly. And none of this stuff depends on Z. None of those terms depend on Z. So therefore, you really have the integral over Z, which gives you L. So on the right-hand side, you really get L again. Now I can integrate this by parts again it's kind of boring, but it happens again, so why not do it again? Why not? More practice. And X and Y can be interchanged to get the same answer. And I probably, yes, I made a mistake. So here, this is the minus. when you substitute these terms here. And this is minus, sorry. This is minus here. So therefore, the moment ml equals minus L G alpha double integral, and this is equal to 1. And also that happens for x, so you get two of them. 2 C, but that's a minus sign, so that's a minus dA then you have this term here, which is the counter integral now, and that's C yeah, I mean, it's correct. And I have the, sorry guys, getting confused with this coefficient here that I'm missing. I need to keep it there somehow. Okay, so everything is there. But again, C is 0 at the boundary. And so now I actually get an expression for the moment, which is very simple as twice G alpha double integral C dA. That's very interesting. I now found an expression also for the moment. So now I'm kind of set, and this actually kind of is taking me somewhere now, because now I have a Laplace equation. Sure, I have a boundary condition for that, which you can actually solve if you're given a problem. And not only that, now I have a moment calculation in terms of the rate of twist. And now also, if I can find C, I can plug it in and get the moment. It's not something I could do when I use the principle of virtual work. When I got this Euler Lagrange equation, I got this moment, and I really don't tell you how to relate moment to twist. I mean, can somebody tell me? Because I don't see how you can actually proceed forward. While with the complementary energy functional, by satisfying the stress boundary conditions exactly, by plugging that in and making C exactly 0 for the tractions at the surface, what I've really done, come up with something clever that allows me to relate, not only get the total potential energy here, the complementary potential energy, but when I look at the Euler Lagrange equation, that's a Laplace equation which you can actually solve with a boundary condition around the boundary, which is C of 0. And not only that, now I also have a way of relating moment to the rate of twist. Meaning, if I apply a moment and I know C, I can actually calculate how much twist I'm getting by applying a moment. Okay, so the question is how you solve for C, right? Well, you have two options. You can solve this exactly because you have the differential equation, partial differential equation. You have the boundary condition. You can go ahead and do that. Another option is to say, okay, take an elliptical cross section. As an example. So say I have an elliptical cross section like that, and that's a tube I want to twist. I want to twist that. So let's look at a practical problem here. Okay, I want to twist this, so I want to twist, apply a moment. That causes a torque to this bar that has an elliptical cross section. And I'm stalling because I'm trying to remember what are the next steps. But In reality, I'll remember as I work it through because that's how this works. Sometimes I don't have the notes for this stuff. So this is X and Y, and we're going to apply a twist here, moment M. And oh, I remember now because this distance here, we know is 2A. This distance here is, let's just come up with cross sections here. And you know the equation of this curve. The equation of this curve is x squared divided by a squared plus y squared divided by b squared equals to, I believe, 1. Let's try it. At x equals here, yeah, I get 1. Here, I get 1. Here, I get 1. Here, I get 1. So that does work out. That's what I have. And so now all I have to do is select a trial function. I know that C is 0 at the boundary. So very simply then, C equals M. I don't know what M is, some constant. Let me call it, I don't like the value M. Let's call it, well, I have to use M because I don't have any other choice. I have x squared divided by a squared plus y squared divided by b squared minus 1. That's all I get here. Now, if you look at this carefully, I think you will agree that this satisfies the boundary condition exactly. So at every value here in the boundary that I select and I plug in here, C will be 0 at the boundary of the ellipse. So it's a little trick. If you know the equation of the ellipse, all you have to do is that. And sure, that'll work perfectly. Now this is cool because I can substitute this stress function into what? Into this equation here. Wasn't that equation that I got earlier? Yeah, that's the equation I got earlier. So now if I substitute that equation in here, I should be able to calculate M. Now, I want to do it with you because I don't want to make a mistake. So why we don't do that? So it's a lot of work for me, but I think it's M 1 over 2a squared plus 1 over 2b squared and that's equal to minus 2. So then I get a value of M of 4a squared b squared minus divided by a squared plus b squared. So I made a mistake when I calculate the gradient of the second gradient of C, you guys should get a 2 over here and not in the denominator. So 2 and 2 cancels out, and then you get M of that. That's what you get. But now that I know M and I know C, now I know C. So I know how C looks like. So actually, now that I know C, in fact, I know stress now. I know stress now because I know what the stress is, sigma xz equals, we said it was going to be what? Well, let's calculate sigma xz later. Let's do this step first. Let's find, I know C, so I can now calculate moment. Because if I know C, I can calculate moment. So that's your C. And I know M now. When you do that, and I know the answer to this, so you should get when you because you can integrate this in mathematics. I don't want to do it here. It's just integrating over the cross section. It's an algebraic problem, mathematics I can do. I'm going to show you how to use mathematics in a second for this kind of problem. So this is going to be G pi a cubed, and I know it because I worked on elliptical cross sections before. A squared plus b squared times alpha. So the cool thing about this, we actually found the torsional constant for this problem. We're able to the torsional constant J. I think you've seen that before. I'm going to define this as J. So you have a circular cross section for circular. Which will match a book on this. So if you apply a moment, now I know exactly how much rotation I get because this is a property of the cross section. Right, that's a property of the cross sections. That's an easy calculation. I know the geometry of the ellipse, the cross section. So I know J exactly. I know G from testing. So basically, I know how the moment, when I apply a moment, I know how much it's going to twist. But not only that, I can actually calculate J itself, which I just showed you how to do, which to me is exciting to be able to do that for an ellipse. You may have used more complicated methods before. And now what I'm going to do is I'm going to take this further and I'll say, okay, I want to now calculate the stresses, which is actually even more cool because now I actually can calculate stresses on this ellipse. I can tell you what the stresses are everywhere there. How do I do that? Well, I know sigma xz is derivative of C. Well, it was what? G alpha? I have to look back at what I assumed. G alpha sub C comma Y. And sigma YZ equals minus G alpha C comma X. And the stresses are going to be, you can write them in terms of moment if you wanted to, and it's going to be minus 2 my over pi ab cubed, and then you're going to find this one to be 2mx pi a cubed b. And so the maximum stress is going to be at the boundary. And the maximum stress is going to be in the minor axis. It's going to be here and here. You've been asking how I got this. Well, I know why, C already, because I calculated M. So it's just simply plug it in. And when you do it, you're going to find this equation and this equation. And the maximum stress is going to happen here and here. Sigma max is going to be 2m pi ab squared, which is actually very, very cool that we found that. I think it's really, really cool. But I'm not done yet. I can now calculate the warping function. So I want to remind you that we selected an approximation of this manner, right? And m is unknown. And it works because x squared and y squared, they become constants when I take this gradient. But if I had selected more terms in this approximation, then you won't be able to calculate m this easily. But I'll show you in an example later how to do that. The question I have now is that now that I took this ellipse, cross-section ellipse, and I torqued it, I know now how to relate. We can relate m to the rate of twist, which is really cool. And I can calculate the stresses in the cross section. So yeah, but hey, what is a warping function? Which, if you remember, I had said the warping function w y z is going to be equal to the warping function. That's what I said. Did I say that? Did I say that w was kappa? Yeah, I said that. And I said that that warping is going to be the same. Doesn't matter where you are along the length. It's going to warp the same. So how to do that, you have to now go back a little bit in time to remember how to do it. First, what you want to do is calculate the strain. And the strain is really, we did that before. I remember doing it before. It was a partial of kappa respect to x minus alpha y. I remember doing it because we took this partial here. We took partial of u respect to z plus partial respect to w respect to x. I remember doing that. And so that term is this term, and that term is this term because u was equal to the minus alpha yz. So that's how I remember that. That's the way we did it. Gamma yz equals is going to be partial kappa respect to y, and then that was plus alpha x, and that's because partial u respect to z on this theory, and that's an error. Yeah, like that, because v was alpha xz, that's why. And so this term here is taking partial of that, and then this term here is that term. So yeah, we got it now. Now we can use Hooke's law, and we want to use Hooke's law to substitute what the shear strain is, what the shear strains are. I'll just write it here. But I know what sigma xz is. I know what that is. Sigma xz, we said it was g alpha. G cancels out. So you have alpha, I believe. You know, there, yeah, I think it was like that. Partial C. Well, let me look it up. I'm getting confused now. I can never remember this term. G alpha C comma Y. And there's a G here, but that's divided by G. So G cancels out. And that was minus, I think. So therefore, now you have everything in terms of Z. If you notice, you have Very nice. And I know what the torsion function was because I found this torsion function. This torsion function was found, psi. So I can calculate what psi comma y is. I can calculate what psi comma y x is. And all I have to do now is integrate for kappa. Just integrate. So substitute psi here. And here. And integrate to find kappa. And I know what the answer is because I have a book on this. Um, I don't want to integrate it right now, but you will get kappa. And what is cool is that that is kappa there. And you can see that if I have a cross section that's a circle, B equals A, so this you don't have any warping. So if you have a circular cross section, there's no warping, which is interesting. The other interesting fact is in this ellipse. You can see for yourself that W is greater than 0 here because X, Y is positive. And then W is negative here because B is smaller than A. And you can see here very quickly that W is greater than 0, W is less than 0 here, and W is greater than 0, which clearly shows you that it's going out of plane. It's going out of plane clearly with that equation. So look at the excitement here. The excitement in here is that I was able to use the Euler Lagrange equation. In this case, I use the Euler Lagrange equation. In this case, I use the Euler Lagrange equation, and then I calculated a formula for moment, right? So I calculated the formula for moment. I'm cleaning this up so that later you don't have a mess. And then I wanted to solve a problem. And okay, I went in and tried to solve it. I could have added more terms, but I stuck to this. And cool, I found the moment for an elliptical bar as a function of the rate of twist. Not only that, I'm able to find uh, the torsional constant, which you've seen in other classes, but I did it using this technique. And then not only that, I was able to find the stresses. And not only that, I was able to then find the warping function. But the question becomes, what do you do if you have a more complicated problem? What if I give you an airfoil? What are you going to do next? So in this airfoil problem that I have, trying to solve this exactly probably is a lot of work. What if we use an approximate theory to solve this equation? But before I tackle the airfoil problem, what we then solve really quickly is square rectangular cross-section problem. And we are given, or I already derived for you, the pi star. We know what pi star is. So I can just use that. We already derived that. And my boundary now goes from, say this is x, and this is y, and this is 2a, and this is 2b. Clearly the boundary goes from minus a to a, minus b to b. So that's very easy. And then I have 1 over 2g c comma x squared plus c comma y squared minus 4c, and that's correct. I don't remember Yeah, I think I had something more like G alpha squared. There's many ways to slice this cake. Um, I'm gonna stick to my notes. I believe it was G alpha squared divided by 2 is what I was using earlier. Minus 4 psi d area. Okay. Why we don't instead of solving the Euler Lagrange equation implied by this Euler Lagrange equation implied by pi extremizing pi star is this. And I don't want to deal with solving that. I want to use an approximate solution instead. And so I'll choose an approximation function that satisfies the boundary conditions exactly. But we know that the essential boundary conditions in this problem is that C specified at the boundary. C, let me call this boundary C. So C is 0 at the boundary. So all I have to do is select an approximation function that is a good one. And I'll select something simple. Um, and this works really well because at x equals plus minus a, C is 0. At y equals plus minus b, C is 0. So this satisfies the boundary condition exactly. And all I have to do is to plug in C into this equation. That's all I have to do. We will use the Ritz plug in C in pi star, and let me make it approximate, so that now all we have to do is partial pi star respect to the constant C1 and set that equal to 0. That's all I have to do, which is beautiful. In our derivation of pi star, I recall uh, I've been corrected, and pi star had a L. So I'm gonna bring the L here, but I could just make it 1 if I wanted to, because it's per unit length. It won't matter. Um, I'll make it 1 to be consistent to the notes. I apologize for that. And now what I'll do, I'll go to Mathematica, and I'm gonna create a functional pi star, which is G. I'm gonna make G, so G times alpha squared times L divided by 2, integrate, and we have to integrate twice. And I want to create this function called C. This function called C, I have selected a constant C1 with a length like that. I'm just doing really quickly so you can see how it's done in Mathematica. That's the function I selected. So all I have to do now is to evaluate an integral that takes the derivative of C, and I want to evaluate the integral, the derivative twice. So it's 2 derivatives there, I believe. And we want to square that quantity, whatever that is. Yeah, that looks good to me. No errors. Minus 4 times C. And my first integrate goes from, and my second one, oh, minus A to A. That one goes from minus b to b. I doubt this is going to work because I'm really rushing it here. And I just don't know if it's going to work out. But why wouldn't I just calculate and see what happens? Okay, no complaints. So solve the derivative pi star respect to C1 equal to 0. And I want to do a full simplify here. So it kind of simplifies all the expressions. It does it very nicely sometimes. Sometimes it doesn't, but it's worth trying. That looks nicer. And so we'll just solve for the constant pi star, and hopefully will give us an answer. And that matches let's see.
I don't think you told it which variable to solve for.
So I knew I did something wrong because this is not the answer. And so I clearly made a mistake. It's only one derivative. And thank you for correcting me. One derivative. And now I should get the answer that I expect, which is 5. I believe it's 5/4 or something like that. Yeah, there you go. That's the answer. I appreciate your keen eye in finding the error. But that's in fact the constant for C. And now I'm ready to take D, calculate, say, the torsional rigidity, which is M divided by alpha. I can calculate M divided by alpha, or I can calculate the moment as well, if you want, regardless. If I know, yeah, I can just calculate the moment. Just calculate the moment equals twice G times alpha. And now I have to integrate again over the domain. And so I can I'll borrow this really quick. It's not correct, like it's not all this, but I'll just do this to save time. And all I have to now integrate is C in here. Just trying to save time. So 2G alpha, and I have to integrate over the cross section. And when I do this, it doesn't know how to do it. Yeah, so I get something here. Oh, it didn't plug in C1. We can plug in C1. Let's plug in C1. Okay, I need to make this equal to something. Solution. And I have to make sure I'm picking the right thing. So he knows. Okay, yeah, I picked the right thing. So I'll now take C1. Oh, I don't have to do that. I can just do this. Yeah. So now I'm going to evaluate it at this solution here. No, I guess I have to do it. Sorry about that. No, I'm doing it correctly. Oh, that's correct. So, okay, I know what's going on. Oh, there's a dot missing. There you go. Yeah, so that's your bending moment. Sorry, the torsion applied, and so torsion divided by G alpha gives you J for this cross section, which is 40 A cubed B cubed divided by 9 A squared plus B squared. What I can do, I can get fancy. and I can add another term if I wanted to. If you want to add another term, it needs to be a constant. So it needs to have, so you can add more terms to this approximation. So I can do approximation 2, but I won't solve it here right now. Just showing you approximation 2 will be C1. And what you can do, it needs to satisfy the boundary term. So you can add term C1 plus C2 x squared, y squared will be your next term. And you may ask me, why am I skipping term? I told you not to skip terms. I told you not to do this. You know, if you do it correctly, it should be this, you will tell me. But we know that the solution has to be is symmetric about the x and y axis. So therefore, we know that it's going to just have even polynomials to work. But I can have 3 terms, and the third term will be looking like this, right? And I can do the same process. I can plug that into pi star and then solve for all the coefficients. So that's how you do that. And you know, this is not a bad solution, the one I got. It's actually not that bad at all. You can also then find the stress for this rectangle, and you will find that the cross section is a rectangle. So you can find that the maximum stress will be in the minor axis of that rectangle, in the short side, towards the center. So that's to me is an exciting problem. So I can then, if I have an airfoil that occupies the space from 0 to b, so from x equals 0 to x equals b, then you can then go ahead and look at this boundary. This is the boundary of y, so y goes from this side to that side per that relationship, following this equation, and h is known. And here, notice how the stress definition I have has no g alpha. That's okay. That was for me to have. It doesn't matter if you don't put a g alpha. If you don't put a g alpha here, then when you calculate total potential complementary energy, it's going to come out to be 1/2g. So it's going to compensate in some other way. And so the point I want to make is that the important thing is that c is an unknown. That's what matters. And when I look at the approximation function, that's a beautiful approximation function because it satisfies the boundary exactly. C0 is that boundary. You know that because when y equals yc, when y equals that, which describes this boundary like that, this goes to 0. And when y equals that boundary, which is the one here, that goes to 0. So this will be 0 at the boundary. And so all you have to do is plug in c in here and solve it. Once you find c, you can find the stresses in the airfoil. Beautiful. I'm excited. And once you find the stresses in the airfoil, you can actually also find the warping that goes along with that. So a very cool problem. Derivative of pi star respect to A1 is 0. Derivative of pi star respect to A2 is 0. Okay. Give me a minute. So how this could be useful? Well, you can calculate the torsional constant for this beam. You can find J. Normally in aerodynamics, there's a moment that's acting on the aerodynamic center. And usually there's a coefficient associated with that can be found through wind tunnel testing. So it can be useful because it can explain to you what is going on, what the value of J is for this cross section, and can also apply for other problems. But really what I'm trying to show you is application of calculus of variations to a very complex problem. And what I like about this problem is that we pursue the principle of virtual work and we ended in a dead end. And what I like about that is because when you use the principle of virtual work, the ordered Lagrange equations are the stress equilibrium equations. And the essential boundary conditions are kinematic. But then I said, okay, I arrived at a dead end. Do I have another way? So I said, okay, let me use a complementary version now. And when I went to the complementary version, the ordered Lagrange equation turned out to be the kinematic relationships. the essential boundary conditions were keeping C equal to 0 and satisfying the traction boundary condition of that being equal to 0. And so that actually really helped me a lot because I was able to solve a torsional problem um, in a cool way. And really, when I look at this problem, I want to see how important this problem is. Imagine if I told you solve, and I invite any, give me, yes, I invite anyone here to solve this partial differential equation, which is really c comma xx plus c comma yy, the Laplacian. I invite anyone here to solve this for this airfoil in the exact configuration. In this exact configuration, give me the exact solution of C. And no, it's not really feasible. And so we came up, instead of doing that, we say, okay, forget about solving this. Let me start with the functional instead. And by the way, this is not the equation. If you define the Prandtl stress function in this manner, this is not the equation. It's going to look different. It's going to be gradient c squared, and I forget what it should be, but you can do the math yourself. Um, but the bottom line is to solve this equation here is highly difficult, and we don't want to do that. So instead, I plug into this functional that implies that Euler-Lagrange equation, plug in an approximation here that satisfies the boundary condition of c equals 0 exactly, and then turn to delta pi star with respect to A1, delta pi star with respect to A2, solve for A1, solve for A2, and once I have those numerical values, now I know what the stress looks like on the whole airfoil is the beauty of this. Because I know C, I know A1 and A2, I solved it from here. So then I know the stress as it varies there, and not only that, I can calculate the moment because I told you what the moment expression is as a function of alpha. And so if I know that, I can find the torsional constant for this airfoil. So a very neat problem that's very, very practical. So with that said, thank you for your attention today.